because they are very nice resources also of knowledge. So we collaborate together in cutting-edge solutions that can be used by CERN and the worldwide and the Large Hadron Collider community. And it's really designed and created to disseminate knowledge. That's we create reports, we publish articles, we do workshops and seminars. That's why, for example, I'm today here. We have also a very nice program student program that is in the summer. And last year we had in our group, we have 2 Indian girls. And one of them was really, really nice. I mean, both were really nice. But one of them was selected even in the project as one of the best talks when they presented. So saying this, so now I guess you have an overview of what is CERN and why we are using data analytics. Now I would like to show you some of the use cases we have. So the first one, sorry, the first one is the CERN is related with the CERN Advanced Storage Manager. That is called Castor, right? So the Castor system is some mass storage solutions for the physics data files. So that's the data that comes from the experiments. And it is a hybrid system with disk and tapes. You can see that like the size of the storage on tapes is double than the size on disk. You might guess why this is, I mean, we are using tapes because sometimes you might think like a bit like old-fashioned, but there are very good reasons. Well, first, it is cheaper, right? But there are other good reasons that might be even more important, because tapes are much more durable than disk. Much more. Data loss in tapes is really lower than disk. And when you want to keep your data for always, that is a very nice media. Of course, it has some problems. Data access or random access is really bad in tapes. It's really bad. But okay, so this system provides some interfaces to the clients, and they don't know if it is disk or tapes. They see storage. So when they want to retrieve a file, the file might be on disk, so they get the file, no problem. But it also can happen that the file is not on disk and is on tapes. So it has to go to the tapes, take it, copy it to the disk, and the disk returns to the client. Also to the storage. If you want to store something for always, so it will have to go from the disk to tapes, etc. So I guess that you got the idea. I mean, it's more complex, but it's clear that the system will have a lot of transfer data between tapes and disk. And it is important to optimize as much as possible the disk, for example, so you can have always the most used files and everything that is going to be really used. So something that we thought, it's, yeah, you cannot see very nice this, but okay. Something that we thought is, okay, we can analyze those data transfer, right? And if we get a data transfer that we can see, analyze, that is labeled as normal behavior, right? You can then create a prediction model there using that data to train it. And then you put it in place, and then you analyze the difference between the predictions and the real data that is coming on the system. So then you might realize that when you make the difference, if there is a big difference, it might be because there is an anomaly. That's what the anomaly detection it is, and it can warn you that something might be wrong in your system. Of course, also you can use it to optimize performance, but it's very, very important to have like kind of early warning system, something that before everything is a problem, you can really go analyze and see if you can do something with it. For the next use case, I would like to talk about the intelligent data placement for the CMS. That's the experiment CMS. But I have to introduce the grid computing, the worldwide LHC grid computing grid. So what is it? Well, there are more than 8,000 physicists that want to analyze data, not at CERN, but all over the world. They want to analyze data, extract data, do very demanding processes of that data. So you can imagine that CERN is not enough for this demanding of computing resources. So that's why the grid was created, and the grid is a network, a collaborative network of data centers connected, so the users can transmit, store, process, and analyze the data. So how does it work, more or less? Just the basics. It has 3 tiers. One is tier 0, tier 1, and tier 2. And all the data passes through tier 0. Tier 0 is CERN, right? So the data coming from the experiment, it goes to tier 0. It is saved, stored, and then it starts replicating that data to the tier 1. Not all, I mean, it replicates all the data, but partially to different data centers. And that data centers will also do the same, will replicate data to data centers of the tier 2. The tier 2 are usually like universities or laboratories that have nice computing resources. Well, during those, it's not only replicating the data, there are a lot of processing of the data because the raw data is not that interesting for the physicists. They prefer to have some already processed information. But you can imagine here that if you are in the United States and you have to do your analysis, it's not the same if you have your data in a data center very close to you with available computer resources, that if you have it at CERN, even not prepared, and you have to, maybe at CERN there is not enough computing resources right now because there are many other jobs running. So optimizing this might save a lot of time and a lot of computing resources in many data centers. That's why in the CMS experiments, they have something called the data popularity. And data popularity monitors along the time, or tracks all the usage of every file that they have. So they know who accessed this file, how many times, for how long, what did he do, etc. So there we can use analytics to try to optimize the resources, to say, okay, try to remove obsolete versions of data that might not be used anymore in that data center maybe for months. So we can remove that and put data that is currently used. That will reduce the job time in data access and also in the data analysis. So basically it will be something like resource prediction, okay? I have another use case that is specifically for the operation and control systems. I talked some slides before about the accelerator logging service, the LHC accelerator logging service, where we have around 1 million signals defined and data coming from them, like in a lot of data, I mean 50 terabytes per year. So we can use that data, those coming from the sensors, like temperatures or magnetic field strength, pressures from the vacuums, to create a kind of control system health. So we can predict that something is going to fail or is behaving fairly, okay, before it actually fails. So we can try to do a predictive maintenance of those components of those systems. And one specific use case of this would be, for example, the cryogenics faulty valve detection. So the objective was to predict faulty valves before they actually fail, right? For that, for example, we analyzed the aperture order of the valve. So basically, they said, okay, I want to open this valve 50%, but there is a sensor that really measures how was that aperture. That might be 50.1, 50.2, etc. So we made the difference between both, and then that signal, we tried to analyze it, extracting some features from it, and try to predict if it was faulty, not faulty, or unknown. Unknown was because there were some of them that the expert, when they analyzed it, didn't know exactly. I mean, he couldn't say this is a faulty valve or not. It wasn't sure. So for that, you can create a predictive model, a classification predictive model, and you use your training data, and then you try to see how good is your classification model, right? And I would like to have just some additional comments of all these use cases, because now you realize that sometimes we talk about real-time analytics and everything, and I wanted to be sure that we have used what is called the supervised machine learning in all these cases. So basically, we work with the data we know, we tune it, right? And when we know, we are sure, we can go farther. But we train the data sets with the data. We know that this is the right answer. We know that those valves were working properly, and the other ones were working faulty. So, of course, you do that in batch process, we can say, offline. But you want to do that, I mean, once you have something, you want to put it in real time and to have that feedback directly from your system in real time, because if you do it every day, maybe it's too late. For some systems, it's too late to know that that was behaving abnormally the day after, because the problem was already there. So that's something to connect to the stream, that to use also is very important to use some complex event processing, and to have real-time visualization and discovery. The good point is that nowadays there are many new platforms, and every day there is something new. So that is aiming to facilitate the use of all these tools and all these techniques. It provides you with a very quick development and prototype predictive models, for example. And then also you don't have the problem of the language, because nowadays maybe they are in Scala or R, but there are plugins for basically Java, Python, well, whatever you might think, all the most popular languages. And they also provide now things like the complete stack, so you don't have to worry. You download something and you have the complete stack with all the different solutions that you might need for the classical analytics, or the visualization, the storage, everything. And even now, you don't even need to put your server working there. You can go to the cloud and sign up, and you have something working. So that is very good for your start of the analysis and to see if that is what you were looking for. So I think that is all from my side. So I just wanted to share with you what we are doing. And I hope you realize that in case, well, I think here many people will be from IT, but sometimes data analytics sounds a lot, it's very popular everywhere, but in business it's also very popular. But there are many, many use cases that are not business related, that are very, very useful for data analytics. So now if you have some questions.
So any questions for the session?
I have two questions. One is if you can give an overview of what technologies you have used in your modules. That's my first question. Second question, you talked about complex event processing and visualization and discovery. I would like to understand where complex event processing came into picture in your this thing, because you were talking it in the context of predictions of faulty equipment, which I don't know how it ties into complex event processing. Maybe I've got the context wrong. But if you can talk about complex event processing, where you used it, and what kind of visualization tools have you used, is my question.
Okay, so start from the first one. So the first one was which tools we have used for our data analytics process, data analytics use cases. So basically for all of them, we have mainly used R. I don't know if you know the language R that this has. So we have made almost everything with that. Of course, most of the data we have now, it is on relational databases. As I said, also we have a collaboration with some private companies like Oracle. This is an Oracle also partner. And one of them is the Oracle R Enterprise. For example, you can run R directly on your databases, on your relational models. So that is nice because we didn't have to download. You can imagine there is a lot of gigabytes. So in my laptop, I can process that. So you can do it directly on the database and use the parallelism of the database itself. So that is nice. So then So that is one of the technologies. Then the other one was about complex event processing in the sense of in this context. So for example, you can imagine that in very complex systems, the failure of one single sensor or one single machine is maybe not a failure. Maybe it doesn't matter too much for the whole because there are spare systems that, I mean, you might know that you might want that this is maybe behaving weirdly, but it's not a very big problem. So you can, with the complex event processes, you can start going from those small use cases to try to have a better picture of your whole system. So maybe your complex event process is like, okay, if this system starts doing this, plus this other hardware is starting doing this other thing, I don't know, going like up and down in that sensor, plus some, I don't know, 1 minute ago I had another event that was that all my systems starting going down, or I don't, it's making up. So you can start building, with complex event processing, start building a really, let's say, nice detector or early warning system from the bottom to top. And there, it's a very nice technology that you can use. But you can even see it in more, let's say, small context, like this signal. If it does like this, it's not bad. But if it does this, and then next second does again this, and then next second does it. So that's a very nice for even complex processing, because you can put it, okay, if it does this in a window of 10 seconds, that's something I want to know. Okay. I don't know if you have something else, it's okay.
There's one more question from this side.
Hi, Antonio. Thanks
Hello.
for the comprehensive talk. And I have a question. I mean, it's regarding, partly regarding scientific research, and having a background in that a bit. So right from the D0 experiment, when top quark was discovered, to when Higgs boson has been discovered in 2012, what do you see? Like, I mean, big data, does it only cater to infrastructure like predictive asset maintenance or complex event processing to generate alerts? Or can it also help in answering some of the questions, like when you actually, you also do a lot of pattern recognition when you actually have to find out Higgs boson. Because there are a lot of detectors and you have to look at the detector signals, and you see that each particle, they change mass with velocity, right? I mean, you have to see them at different time intervals, at different snapshots, and as you were mentioning about the tapes. So I think it covers all the 3 or 4 use cases you are talking about. And I'm sure there are several other use cases beyond those, which probably you have not discussed. So my question is big data only solving the problem in terms of infrastructure, or is it also helping in the journey on cutting edge scientific research?
Well, then first I would like to be clear in the sense that I've talked also about the physics data because it's one important part at CERN. But what we are doing in our project is not in the physics data. So the physicists made, of course, data analytics. But they have been doing it always. For example, for the discovery of the Higgs boson, they need to analyze and do a lot of analysis of the data, right? But we are in the side of the technology part.